We're ready for our next set of content, but let me just review. I've gotten through about a third of the exams so far. The vast majority of scores are at or better than how you did on test one, some significantly better than test one. I lost track, but just in that first third, there was at least two hands full worth of hundreds, which was nice to see. Um, I have a problem ethically with that one question, but when you get yours back, that I had to do the adjustment on, I think it may have thrown some people off. So we'll have discussions on those. Uh, but other than that, it's looking much better than test one's results were. But so we're doing well. And the good news about that is as we get into test three, so I'm just kind of giving you the whole content, we continue on with a little bit more advanced probability. So this idea of counting how many of those event things divided by the total number of things that could happen, that's really going to stay throughout the rest of the course. And what we build into, so today we're going to do conditional probability. It's just basically the same thing, except we know something already happened. And so that changes, the scene. We know it's raining. Does that mean what does that mean about the streets being wet? Arizona, it's not always 100% chance that the streets are going to be wet if it's raining, right? Because sometimes it evaporates before it hits there. But those kind of things. And just kind of get you into it, these next few lessons will really build on themselves. So it's going to be important to kind of stay on track. Like today, we'll do some things with tree diagrams. Friday is almost all taking that concept and building on it. So you gotta have this one down. You can't just jump in on Friday stuff. It won't make much sense. And the same thing kind of goes on. We do some things with random variables. So that's a probability of something happening. I remember going over those myself. There's two types of random variables. It's a little abstract, but we'll do our best. And as we move in, you'll start to see we're getting into statistics, mean, median, mode, standard deviation stuff, which is statistics is a use of probability, the chance of something happening, and then using those to say what's going on. Is there? So it's really through the rest of the course we're dealing with the same type of concept. So we're not like this last one. There was two different things, right? There was matrices for about half the course, and then there was probability, and they're kind of almost completely different. Maybe they are. This next set, it will all flow together. Okay. Homeworks. I have extended every single homework in the course until May 2nd. So you can go back to any from the first set if you want to complete them. Second set, they're all open. I will be updating those. I have to manually download the scores and then sync them in with the Canvas gradebook. And I use your student IDs to match them up. So hopefully everything matches up. But when I do that, I go back all the way to the beginning. So I will pick those up as they come. I haven't done it for the second set, and some of you said, "Hey, I completed those, and I still got zeros." I'll get that this weekend. So I want to get the exams graded, and then I'll get those updated. So actually, I better get busy because Friday's the withdrawal date. So if someone has a question about withdrawal date, if you're, again, at this point, I really highly recommend just staying in the course. Even if you fail it, you've at least finished it. You'll take it again and you'll replace that grade. But other than that, everyone has their thing. So if you're anxious about or thinking about using the withdrawal date, send me an email and I can at least get you your exam scores sooner and get those updated. But again, most of you are doing just fine. But homeworks, you can continue to go back. But again, I highly recommend, suggest, ask, plead that you stay on track with this. And then if you have anything for previous stuff, go ahead and make those up as you get caught up, because test 3 is only going to be over this stuff. We're not going to test you again over the other stuff. So it's just more a chance to maybe make a few points, but also you're learning some of the previous stuff that, and I don't know what part of this you're going to use. We give you a bunch of different analysis tools depending upon what you end up focusing on, you may use one part or the other. Some of you may do a lot into matrix type stuff, which I'm a little disappointed we didn't have more business applications of it. But that's just how it is. I teach another course where we do a lot more application type stuff of the matrices. But we digress. Okay, so we ready to proceed into today's setting? And again, you'll find, I think that much of this is very, if you were connecting with the probability at the end, this is just a natural flow into it. We're going to use some Venn diagrams. So I'm going to highlight a few things from the last one. And again, we've got this learning activity. I'm going to put exam 2 in that mode so it doesn't bother us. We're just down here right now. We've only got 8.5. I have looked ahead to what we'll do Friday is 8.6, which is going to be an extension of this one. And we'll see how this all works. So conditional probability and independence. So let's just talk about what is a conditional. If I say the word conditional, what does that mean? What are some words that go with a conditional? What's a condition? What's a prerequisite? Something you need to do before. And that's sort of what the conditional is. We know something had already happened. And it's not necessarily quite like a prerequisite that's a requirement. But what we're going to tell you is that if we knew this thing happened already, then what are the probabilities? So we're not just looking at a random case of anything could happen. Oh, no, we know something already happened in this event space. So now what's the probability of other things happening? So it's kind of think along those terms. How about independence? If you're independent, what does that mean? Don't rely on something else. So not being dependent or not being independent means you are dependent, that something else kind of influences you. I know my first choice of college, my dad highly influenced me because I said, I want to go to this school. He says, no, you don't. You want to go to this school. Okay, I went to the school. I tried it the first year. Then I switched over. Went to University of Washington. I wanted to go to Portland State because I wanted to stay home, and I switched over there, and I was much happier. He wasn't too happy, but hey, it's only about us, right? Our parents should be happy when we're happy. Anyway, he finally saw the light. Anyway, so independence is if something's independent, the probabilities will not change because they don't get influenced, like rolling a dice and flipping a coin. The fact that I rolled a 6 is not going to change the probability of you get a heads or tails. So we kind of think along those terms. Those are independent events. However, if it rains in Mesa and it's coming, that may affect what's going to happen in Scottsdale, right? Oh, rain in Mesa, the wind's blowing that way. There's probably a more highly probability that it'll rain in Scottsdale. However, we looked at the one, rain in Hawaii might not affect the rain in New York. So those are probably independent, but it could be, So we're going to look at tools that will allow us to do this. So that's the big overview picture of today. We're going to start off with a couple. Actually, we'll use this example for a few different things. So it all starts off with collected data. So we're doing probability. This is sort of observational probabilities. We've seen what's happened. And this setting is we've got a video game company. They're doing some advertising. They want to promote the launch of their latest game, The Ultimate Hockey Recharged. Any hockey fans? Okay, few. I used to. I didn't want to lose my teeth because most of hockey players I knew lost a tooth or two. So anyway, I couldn't skate very well either. Okay, they want to choose the most persuasive of these ads to run the major social media sites, of course. One of these ads was posted for a week on the webpage of an 800-member gamer group, and the results are summarized by the table up below. So we've got this table. We see there was 100 people that saw the ad. Of those that saw the ad, 20 purchased and 80 did not. Okay, so that gives us a probability. So in this case, we could say there was a 20%, if they saw the ad, there was a 20% chance probability, right? There was an 80% probability that they didn't buy it. Okay. Over here, Those that did not see the ad, we say there was 700 of them. And again, 70 purchased and 630 didn't. And then we've got totals over here of who purchased, so we've got totals for purchase the game over here. The bottom level is totaling whether they saw the ad or didn't see the ad. So this kind of table is something you would see probably quite often in a business marketing. Okay. Now you might say, you just look at it, well, 70 bought who didn't see the ad and 20 who saw the ad, so it doesn't seem like the ad had much effect. But what you have to look at is probabilities, right? So the probability, let's do this. Okay, I'll stick with this one. So what we're looking at is with conditional probability, what we really want to know is what's the probability that they bought when they saw the ad. So we're going to write that as the probability purchase the game as A. And what we do is we use this little symbol here as given that, or if. That means the condition, this condition has been met. So whatever comes after the bar is the condition that was met. And what we want is we want to see, okay, those who saw the ad, what was the probability that they bought it given that they saw the ad? That's how we read that. So we just remember this little bar is given that that happened, or if that happened, right? So conditional is all that. And so the way we just calculate it from this table, okay, we know the total that saw the ad. That's what's happening because it's telling us B did happen. So B happened, not B didn't happen. They saw the ad. So that means our total is now 100. And then what's the happening up here is we want really the intersection of A and B. The intersection that they saw the ad and purchased, right? That's what's going to go up here. Does that make sense? They saw the ad and they purchased. That's what we're trying to calculate. That's what A, in this case, A is given that B has happened. That's how we're going to do it. And so it's just, that's where we get our 20%. 20 divided by 100 is 0.2, but you multiply by 100, you could write it as 20%. So there's a 20% probability. We might want to compare that to the probability that they bought the game, purchased the game A, given that they did not see the ad, which they're doing as B not. So again, so now we're going to see, were they more or less likely? If we just look at the numbers, 70 bought versus 20, so we might think again, hey, they don't need to see the ad. But how many total do we have since not B happened? What is our total? We're doing out of 700 now because we know B, they did not see the ad. So again, it's a conditional. And sometimes we think of a condition that actually happened. Sometimes we think, what if it didn't happen or something? But in any sense, this is now going to be out of 700. And again, we look for that intersection. They purchased the game, but they did not see the ad. There's our 70. So it's 70 out of 700. That's a lower percentage. Anyone got 70 divided by 700? How much? 7%? 10%. Okay. Yeah, I thought it was something like that. Maybe it's one, anyway, something like that. So it's about 10%. So not seeing the ad, actually, now we see as a percentage basis, they were less likely to buy. So those who saw the ad were twice as likely to buy, right? 20% bought who saw the ad, only 10% bought who didn't see the ad. They came across it, whatever. So it looks like maybe that ad was somewhat persuasive. And again, what they're doing is they're marketing it into a group that is somehow, since they're all part of this group, they're probably similar. That's the idea. They might not be, but that's the idea. So we market to just this particular club, and let's see what happens. So this is conditional probability. Okay, and you can also think of it as just, percentages, relative frequency of things happening, but we classify this as probability. So far, so good. So let's also use some symbolism to see what we counted. In this top one, what we counted was the number in B was our total, right? Saw the ad. And in the top, we counted the number in A intersect B. Just seeing these symbols, because we will also turn these into formulas, and so we sometimes we're given things and we could just jump to the formula. So that's all we're doing. But to understand the formula on the table, sometimes a little bit easier. Oh, it's this column and this, but this 20 is an intersection of two things, right? And we're going to see a little bit later, it'll break it down. Had they given us the percentages, this actually ends up being the probability of A intersect B divided by the probability of B. And what is this? Remember what we started with. I'll just rewrite it so we can see these together. This is our formula we're going to be using. We're going to be asked for A given B, and we can use this sort of formula. Okay, so it'll be more formalized, but I just want you to see it now. That's what we were doing close to this. We were just looking at this table and picking out the numbers, right? And down below, the same thing happens. What we did here, we did the number in A intersect B not in B, they didn't see it, divided by the number in not B, B not, which again gives us the same formula, B not divided by the probability of not being in B. That was the probability of A given not B. Okay, so we'll just kind of see, okay, we're looking for the probability A given not B. We're going to divide by the probability of not B because that's the total thing. We know it happened, or at least we're assuming that happened. So that's our 100%. And then the intersection of the two is the overlap. So we can also, if we did this as a Venn diagram, right? This is A, this is B. We're basically comparing the size of this piece, A intersect B, to the size of B, because B is our 100%. Nothing else happened, right? Not B did not happen. Okay, so that's what we're looking at, is this intersection. So we're just basically getting the ratio of those two sides. And so I remember when I learned this, it made sense afterwards, but it was introduced with me with a lot of formulas, and I couldn't understand the formula. So I wanted to start with an example where it makes sense. So we're going to keep coming back to this. So if you can kind of, because two ways is some people pick up on formulas pretty good, but sometimes if it's laid out on a table, you can say, oh, those are the pieces going together. And that took me a long time to put together when I was doing this. Okay, so conditional probability. Now we're so that was a heavy part of the lesson. We're going to unpack that a little bit piece by piece. So hopefully it starts looking. So put it another way, this is the probability of A occurring when the sample space is reduced to just those outcomes in B. So let's just say, okay, forget about everything. The circle B is all that exists because that happened. So what's happening within B? And so this is purchase games given that they saw the ad. Again, just a notation. We calculated as 0.2. So these slides are going to go a little slower over this. The second probability was a probability of A given not B, that they didn't see the ad. Okay, purchase the game given that they did not see the ad, and we came up with 10%. Okay, and so we see it was seeing the ad, 20% bought, not seeing the ad, only 10% bought. Ad seems to be helpful. So how did we calculate this? Again, we've already talked about this. This is just going to review step by step, maybe with a little bit nicer writing than I have. It was the number of members who saw the ad divided by the total number of members who saw the ad. Oh, saw the ad and bought the game, right? So that's that intersection, right? The and is intersection of those two events, and they have that there. Okay, so again, this is what I showed you on the first page, but so it's all on the first page, it's all together. Here it's just kind of talking about. And so we did this. This is a complicated way of getting to these probabilities. So the probability of A intersect B, if you divide by the total sample space, that's this. So it's just showing that I just jumped to this. I didn't put this part because it's messier than it needs to be. You just sort of say, well, if this works, this should work. It does. Okay. And those are the kind of things. Either I will give you the numbers of things, or the homework will give you numbers of things. And so you'll be using this one. So if you, oops. Back up. So if you have the number of things, you're given the numbers, you'll use this sort of thing, how many of this and how many of that. If they give you the probability or the percentages, then you're going to use this formula. And in the homework, you'll see both types of questions. They give you some percentages, and so you could just basically use those percentages directly, or they'll give you numbers. 15 people did this, and 120 did that, and so you could use the numbers, and we'd do both. Make sense so far? Okay. And again, it has to be that the probability has a chance of happening. If it's impossible to happen, then it doesn't really make sense talking that it happened when it's impossible to happen. So probability B can never be 0 because you can't divide by 0. But that just seems, if it's 0%, then it's really not an event, right? So I don't, but mathematicians, we always put those kind of things in there. So probability of A given B. And this is sort of the summary of that whole formula. It's we can talk about it this way, but again, sometimes we need to use this form of it, that it's the number in those intersection, the number in B, because that's the way they gave us the information. Okay. But we can also deal directly with probabilities. So it's not too bad of a concept, but it can be, because we got this new symbol, this slash, and how do you read that slash? A given B. And there's a little bit of problem with, at least this was a problem with me being dyslexic, the order that they write it is I wanted to say A happened and given B. Well, given B, that means B happened. What about A? So to me, it's kind of backwards. So if you find that, just kind of go with the flow and say, hey, they're doing it sort of different. I see it this way, but I can switch it so I match up with what these people are doing. Like in this country, we drive on the right side. Other countries drive on the left side. When you're in those countries, please drive on the left side. Don't try to, we all drive on the right. No, you got to do what got to do what society's saying. So a lot of this, a lot of mathematics is that way. Mathematical society has said we go from this way to this way, and we understand the concept, but if we're trying to swim upstream, it just makes it hard on ourselves. Okay, and this is kind of the crux of what we're doing, and a lot of things will just kind of build off of this. Here's what it could look like on a Venn diagram, right? So we're just, again, the blue has happened. So this is saying B, we know blue has happened, so we could really ignore anything outside that circle because we know B happened. And we know that's all there is inside of B. So since B happened, what we're looking for is this overlapping place. That's where A also could happen. A can't happen over here, right? This is in A naught. So that, but it's we do know the whole blue thing happened. We're saying, okay, what part of that blue circle also includes some stuff from A? That's all we're doing. That's all it is. So visuals sometimes are helpful. Formulas are sometimes helpful. And we're going to see through these next 2 days, today and Friday. Friday is very related to what we're doing today. We're just kind of going to go back and forth between visuals and formulas and numbers and probabilities, that they all will work the same way. Okay, so here's an example. There's a 50% chance of rain and a 10% chance of both rain and lightning. Okay. L, then the probability of lightning given that it rains. So again, we could also kind of visualize this. I want to do this. So we'll call this rain. We'll call this lightning. Now there's a 50% chance of rain and a 10% chance of both rain and lightning. Now, one of the things I've seen in the test is some people would want to put 50% here in R, but remember this overlap region is also part of R. So we actually have to go to the middle part first. That this middle part is 10%. I didn't make it, I never make my intersections quite big enough. You have to make them a little juicier. Anyway, 10% there, so there's actually only 40% here. See, this circle has to total 50%, right? So it's 40% of rain alone, 10% of rain and lightning. That makes the whole thing. Now, how much is in lightning? They don't give us enough information, and it seems like it doesn't really matter, right? Because we want the probability of lightning given that it rains. All we care about, that has happened. That circle really is all, we don't care about this side over here anymore. We want the probability of lightning given that we know it's already raining, right? And so the fact that there's only a 10% chance that we're going to get lightning inside this rain circle. Again, there's some probability over here that we got lightning without rain, but we don't care about that because we got rain right now. Okay, and so when we think about this, right, it's the probability of the intersection, lightning intersecting with rain, divided by the total, the probability of rain. And so we're going to get 10%. Now this is where you got to be careful. What's the probability of rain? Be careful. Don't pick out this 40%. That's only the probability of rain without lightning. It still is this 50% total chance of rain. 50%. So that's going to give us 1/5 or 0.2 or 20% chance, right? And I think they go through these steps. But that's the idea is we're looking for, you could draw, a lot of this you could do it visually. So if you're visually oriented, you might find using the Venn diagrams very helpful for how you do it. And that's how I started. I use those a lot, and that helped me understand the formulas. Others of you might find the formulas more understandable, and then you'll work the other way. Oops, I wrote on top of what I had, but let me just, oh, I was supposed to write on the left side. I forget. See, when I set these things up, I forget where I put myself some work. L intersect R. So this is the same thing I wrote. 10% divided by the 50% gives us the 20%. Okay, 20% chance of rain. And the way to think of it, if it rains, the probability of lightning is 20%. So there's a greater chance of rain if it has a greater chance of lightning than if it rained, right? I guess. We know it rained. So there's now a 20% chance. So that's why they said if it's a rainstorm come inside, it might, there's greater probability of lightning. Also, assuming that it rains, there's a 20% chance of lightning. So, yeah. Now, originally, it was only a 10% chance that they both happened together, but that's the whole events. Conditional means we know something happened. Now there's a different probability. Making sense? Okay. Here's another example. Let's go through a few of these. Yeah, we could do this. Bureau of Labor Statistics is founded as if a graduate, and again, conditionals a lot of times, this word if is going to be used in the conditional. If a graduate of the 2020 graduating class went on to college, there was a 28% chance that he or she would work at the same time. On the other hand, there was a 63% chance that a graduate would go on to college. So notice that's not, 63% is not conditioned on anything. just in general, there's a 63% chance they went to college, but this 28% chance is a conditional. If they graduated and went to college, then there's a 28% chance that they will work. So what is the probability that a graduate would go on to college and work at the same time? Go to college and work. So let's see. It was all clear last night. Let's so on the other hand, there was a 63% chance that a graduate would go on to college. So bless you. Hopefully I'll get my circles in the right place. So this is maybe a graduate goes to college. This would be that a graduate works. And this middle part here is they went to college and they work. So that's the intersection part. So let's see if we can fill this in. There's a 28% chance that he or she would work at the same time if they graduate. So 28% we know is sort of in this. Does that make sense that it would be in the intersection? If they graduated, so they're going to college, then those people would work, about 28% of them. Now, we don't know how many didn't go on to college and worked, but we don't need to because we're going to see the question. Well, maybe we do. I don't know. Let's see. On the other hand, there was a 63% chance that a graduate would go on to college. So again, it's not 63% here because we've already got 28. What would be this part? It would be 63 minus 28, 35. Thank you. My mind was not going to go there. And we can put percentages on these, right? And again, I guess since the statistics are probably only considering graduates, because if they didn't graduate, they probably dropped out and they end up not being in the statistics. We could probably assume that the rest, that this should probably add up to 100%, that there'd be nobody outside of this. But I guess there could be, they could have graduated and not worked, right? That happens. That happened to me. I couldn't find a job, so I didn't work. I was looking, but I wasn't working. It took me a long time. I was a depressing time. So there could be some outside here. So what is the probability that a graduate would go on to college and work at the same time? Go on to college and work on the same time. So notice that's a 28%, but this is giving us sort of a conditional, the probability that the graduate would go on to college, that's the condition, and work at the same time. So what we're really talking about is a probability that they are working. Notice how it's sort of backwards. That was the last thing, saying, and work at the same time. What's the probability that they work given that they went to college? Does that make sense? Okay, so that's sometimes translating from the English to the math. Again, you see how it's sort of backwards when we think through this thing. But the given, the condition, is that we're only considering those who went on to college and then they work. So what would we do? Well, what's the percentage that went on to college, right? So this really becomes the probability of W intersect C divided by the probability of C. And again, we did this, we were careful about the 35%, but then when we use the formula, probability of C is this total, which was up there, is a 63%. So sometimes using the formula is a little bit quicker. I didn't have to do this extra calculation to figure out, what was only in C. I can just go, oh, there's 63% here, and they told me there's 28% there. So that's all I got to do when I kind of go with the formula. And what does that give us? (28) divided by 63. 0.44 or 44%. So see, a different thing is you hear 28% went to college and worked. But actually, of those who went to college, 44% of them are working. So that's a larger section when you think of it that way. When you go, and that's sometimes in arguments, like labor disputes and stuff. People are drawing different things. Someone's talking about conditional probability, the other's not talking about conditional probability. So they're both telling true facts. Both could quote like the 28% or the 44%, but they're going, wait, which one's true? Well, you have to see the context. They're both sort of true. Usually one of them sort of doing some white lie type stuff because they're not being honest. They want it to look lower or something for their political gains. But watch it, they could be telling a truth, but they're not telling the truth we think they're telling us, right? So both are true. Okay. Now this is basically just a little algebra. So we talked about the probability of A given B is the probability of the intersection divided by the probability of the B happening, which will be given. And if we multiply both sides by the probability of B, we can rewrite this. And I don't know, there's this thing, right? Notice how this formula has changed. I would just multiply both sides by the probability of B. But so then that means I would, instead of writing it this way, I would write it switched, how they kind of changed it on us, that the probability of B times the probability of A given B is equal to the probability of A intersect B. So they're exactly the same thing, but it's just how they changed it. And again, for me, this was a major thing because I couldn't follow it because they were also switching the sides on us. And it slowed me down and actually prevented me from understanding. But when I do this thing, it's a lot clearer. I say, oh, they just multiply both sides by the probability of B, and this is still in the same form. What they did is then they did a swap, which you can do if two things are equal, they're equal the other way. But it's just a little bit more difficult for me. Okay, so we're going to use this. This is called the multiplication principle of probability. So when we get to the formula, sometimes because of the way it's set up, we want this, and we're given these two, so we just multiply it. Sometimes when we want to find out what that conditional is, we're given the other two, so we use that one. So it's just like, the thing is, you could remember one of them and just do the algebra if you're okay with that. If you don't like the algebra, remember the two different formulas. That's sort of how I did it. A lot of statistics class will let you bring in a page of formulas, your own personal. I had these on my page of formulas, and then I could, what are they giving me? It told me which formula to use. Okay, so it's also used in connection with tree diagrams, and we're going to take a look at tree diagrams, which is nothing new, but it's, again, we're taking the same concepts and we're just using a different way to understand those concepts, which is going to empower us for Friday, because we're going to start looking on Friday. We'll do the same thing with two events, which is not too bad. But what about 3 events? And again, just to get you there, like for insurance companies, there could be 3 things, not that you had an accident or didn't have an accident, but that you had a minor accident, you had a serious accident, and you had a catastrophic, so there could be 3 different things, or maybe 4 different things that they're looking at. And we're going to be able to see that this tree diagram is going to be able to take us further and get us into those events where there's more than just 2 things happening, which is usually the real world, right? It's not just this, rain or not rain. It's, you get rain or did you really get rain, right? Those, what do they call those air rivers? They got a name for it. So here's what a tree diagram looks like. So we start off with the conditional that we're given, right? So they saw the ad. So here's B. Yes, it either happened or it didn't. And what we're going to do is we're going to fill in the probabilities. And I think we'll do this from the totals, and you'll be able to see we get it. And then once B has happened, either A happens or A does not happen, right? So that's kind of branching off, just thinking of this as decision steps. And we're going to see the same thing ends up happening. And if we go along each pathway, we get here, this becomes the probability, or the pathway of A intersect B. This one down below, this pathway, if we follow it this way, gives us A not intersect B. And the same thing happens down there. So we can actually calculate all the different probabilities. And at the end, these 4 different events of A happening or not happening, given B and all that stuff, those have to all add to 100%. Okay. And so sometimes this is going to be a little easier to walk through. So let's kind of go to the next one. And there's a couple in the homework where they give you the tree diagram and they want you to fill in the blanks along the way. Okay, so for this one, let's see if we can do this. For instance, the probability of traveling up the branch from the starting at the B node is 10 out of 800. So again, we're looking not so much at the conditional. So here's B. Here's not B. And what we have is B is 100 that they saw they add divided by 800, right? 100 divided by 800. So this is a 12.5% chance that B happens. And again, we've got it either happens or it doesn't. So what would be the probability of B not happening? Well, you could see that would be 700 divided by 800, which, or take 12.5% minus 100, and that is 80, 70, 875. Is that right? Okay. Should be able to do these, but it's just kind of, so we can do that. And then from each of these, we'll draw the, so if they saw the ad, A is they purchased it, A not is they didn't purchase it. And again, we can calculate that. So what's from B, if we're, so again, we're here, this is the conditional, 20 divided by 100, this will be 0.2. And that they didn't buy it would be 0.8, 80 divided by 100, right? So notice each branch adds to 100 because it either happens or doesn't happen. So that's the whole thing. But then if we're interested in the conditional, the probability of A, that's really what this one ends up being, given that B happened, right? That's this branch, we can just multiply the two together. 0.125 times 0.25. And that's really this, remember this 0.25 is a conditional, actually, I got this backwards, don't I? Call this the probability of A intersect B. This 0.2 is actually the probability of A given B. So let's label this. This is a probability of B, and this is the probability of A given B. And so we can calculate the intersection by multiplying these two. And what's 0.2 times 0.125? Anyone? .025. So about 2.025, about 2.5%. So see, we can actually get, remember this from the tree diagram, this is giving us the probability of the intersection. Okay, because sometimes they don't give us that. And actually, if you wanted to think of this, this is the probability of A intersect B. If you took 20 divided by 800, we could actually do that directly, right? That should give us 2.5%. And I hope so, because I haven't tried it in advance. And sometimes, okay, good. So that's what's supposed to work. And sometimes you do this enough, you have this kind of, you're going on faith. It will work. Who says there's not faith in the sciences? Yeah, you got to have faith. Okay, so that does work. So again, that's how I sort of I could always go back to the table, and all these calculations are just different ways of taking this and this as a total and going. So the intersection is 0.25, which is, that's the intersection of 20 out of the total. Okay, so we could do each of these branches. I'm not going to, we're running short on time and we might not get to, we're almost there. So let's see. Actually, we'll have to, I think we'll wait till, for Independence is not too much, but we'll pick up Independence Friday and then go right into, because Friday is primarily dealing with tree diagrams as well. Okay, so this is the full tree diagram, and you see the 0.2025. But all they're doing is they're multiplying along the pathways. So we go here, here, and notice they multiply those two together. That gives us the intersection of these two things happening. If we go here and down this way, again, we're multiplying those two. There's a 10%, and so forth and so on. And if you add all these on, you're going to get 100%. You know, I didn't do it, but I have pretty much faith that that's the way it's supposed to work. So it should be. You give it a check. Okay. So you start seeing how all these pieces fit together very nicely. But there's a visual way to understand it. There's a formula way to understand it. And they kind of intersect with each other. I think, yeah, we're right. This is a good place to start. We're not going to rush into the next 4 or 5 minutes and try to talk about independence. We'll pick that up Friday and then naturally come back to tree diagrams for that next Bayes theorem, which is just a use of it. Okay, so, and this is not too bad. Thank you all. And again, the goal is I'll get everything updated over the weekend, and so I'll be able to hand back exams on Monday. Got a couple still doing makeup tests, so Monday we'll count on handing back exams. Be here if you want it. If you don't, if you're not here Monday and you want your exam, tell me when you're going to be here and I'll carry it. But I won't keep carrying all of them with me every day for the rest of the course. So Monday I'll have them all, and then if you aren't here Monday, let me know and I'll have your copy on another day. Thank you.